All right, let's dive right into this explainer. Today, we're talking about the high monochromaticity of laser light. We're drawing on some absolutely fantastic insights from physics Vidyapith to figure out what actually makes laser light so uniquely powerful compared to, say, that regular old light bulb sitting on your desk.
We've got a really great roadmap for you today. First, we'll be defining monochromaticity, then comparing normal light versus lasers, before measuring light purity, and finally looking at lasers in the real world. So, let's get to it.
But before we get bogged down in the heavy physics, I want you to just stop and think about a profoundly simple question. Is any light in the universe perfectly pure? It's kind of a wild place to start, right? But the answer might actually surprise you, because looking into this reveals the fundamental physical limits of our universe.
All right, moving right along to Section 1, defining monochromaticity, the quest for spectral purity.
So our core concept here is monochromaticity. If we break that word down, mono obviously means one, and chromatic relates to color. So formally, it's the degree to which a light source emits radiation of a single wavelength or frequency. You'll often hear scientists call this its spectral purity. Now, while a laser beam is highly monochromatic compared to normal light, what we're really talking about here is a measurement. We're measuring just how incredibly focused, stable, and uniform that wavelength actually is. And our source points out something absolutely fascinating here. Absolute monochromaticity, meaning the spread in frequency, or delta nu, is exactly zero, is an ideal condition. But it's physically impossible to achieve. Literally, perfection does not exist in practice. But hey, here's the exciting part. Lasers give us the closest possible approximation to that perfect ideal that human beings have ever created.
Which brings us to Section 2, normal light versus lasers, the Great Divide.
Now notice the stark contrast between these two examples. Look at a normal monochromatic source. The spread of light ranges over a wavelength on the order of 100 to 1,000 angstroms. Basically, it's spitting out wave trains of really short duration and length. It's messy, a totally chaotic burst. But then look at the laser source. The wavelength spread is less than 10 angstroms. There's no contest. Instead of those short, chaotic bursts, the laser emits continuous waves of very long duration. It's highly organized, neatly structured light. But remember that idea we talked about earlier? Perfection just isn't possible. So the crucial point here is that even lasers have a messy limitation. The actual mechanism that determines a laser's ultimate spectral line width, the thing that literally stops it from reaching a perfect zero, is the random spontaneous emission happening right inside the laser cavity itself. That tiny, unavoidable bit of randomness, that's the physical boundary of light purity.
Okay, moving on to Section 3, measuring light purity, the math of monochromaticity.
Let's lay out the key variables we're going to need. First, we have our central frequency, which is represented by nu0. Then we have our line width, delta nu, which represents the spread we just talked about. And then we have two absolutely crucial concepts: coherence time, which is the duration the wave remains continuous, and coherence length, which is the actual physical distance that wave remains continuous. All these variables together, they're the building blocks we need to calculate what scientists call the degree of non-monochromaticity, represented by the Greek letter Z.
And here is the core formula. To find that degree of non-monochromaticity, which is essentially asking how impure is this light, you just divide the line width, delta nu, by the central frequency, nu0. So what is this equation actually telling us? Well, it shows that as the line width approaches zero, the value of xi also approaches zero. Basically, the light is getting closer and closer to that impossible ideal of perfect spectral purity.
But actually, we don't just have to use line width. We can also express this degree of non-monochromaticity using those coherence variables we literally just looked at. We can relate it to time, where c equals 1 over the coherence time multiplied by the central frequency, or we can relate it to distance, where c equals the speed of light, c, divided by the coherence length multiplied by the central frequency. What this brilliantly illustrates is that evaluating a laser's purity is directly tied to how long in time and how far in space the light wave manages to remain perfectly synchronized.
And that brings us to the golden rule of this whole concept. This relationship reveals that the longer a wave can travel without breaking its continuous structure, so a higher value for coherence time or coherence length, the more highly monochromatic or pure the light is. It's a direct, totally measurable relationship.
Let's see this in practice in Section 4, lasers in the real world, the ultimate example. Let's take a look at the specs of a high-quality helium neon gas laser. This thing provides a truly spectacular example.
It features an extremely tight bandwidth, that delta nu we mentioned, of just 500 hertz. Now, for a light wave, that is an incredibly narrow spread. And because of that tight spread, it boasts a coherence time of 2 times 10 to the negative 3 seconds. I know, that might sound like a super tiny fraction of a second, but for a wave traveling at the literal speed of light, that translates to an unprecedented coherence length.
600 kilometers. Seriously, just think about that massive 600-kilometer figure for a second. That incredibly tight bandwidth of 500 hertz translates to a staggering coherence length of 600 kilometers. This means the light wave emitted from this laser stays continuously organized, unbroken, and perfectly synchronized over a massive distance of 600 kilometers. No way, right? But that is the real power of high monochromaticity.
So why does this all matter? Why do we care about a wave staying organized for 600 kilometers? Well, because this high spectral purity leads directly to massive real-world applications. Because lasers can maintain this kind of incredible purity, they unlock our ability to perform highly delicate, hyper-precise tasks. We're talking fundamental scientific research, photochemistry, and complex techniques like luminescence excitation spectroscopy and Raman spectroscopy. And perhaps most importantly for us, this incredible wave organization is literally the backbone of the global communication systems that connect our entire modern world.
As we wrap up this explainer, our source provides a pretty profound caveat. No light source, including laser light source, is perfectly monochromatic, but a better approximation to the ideal condition may be considered in the case of the laser beam. Basically, perfection is a myth in physics. The universe has hard limits. But human engineering, through the development of the laser, has figured out how to approximate that perfect ideal brilliantly. We've literally taken chaotic energy and organized it to push the very boundaries of what is physically possible. And that leaves us with a final thought to ponder. If absolute, perfect monochromaticity is impossible, what new technological frontiers are we going to unlock by pushing our approximations even closer to perfection? Like exactly how much closer to absolute zero can human ingenuity push the line with? And what brand new secrets of the universe will that next level of purity reveal? Thank you so much for exploring the incredible science of laser monochromaticity with me today. Keep asking questions and keep exploring.